Hello students, welcome to the video on power dissipation and harmonic distortion in class B push-pull amplifier. First I'll start the power dissipation concept. Formula for power dissipation, PD is equal to PDC minus PAC. What is the formula for PDC? In the last video I derived the PDC. PDC is VCC into 2Im by pi. What is PAC? It is Im by 2. Okay, now we will write Im in terms of Vm. Im is Vm by RL. So if you write like that, 2 VCC into Vm by pi RL minus Vm square by 2 RL. This RL is the load resistance of the primary. The transformer connected to the collectors of the two transistors. Okay, if the transformer is ideal, the load resistance for primary and secondary is same. As the transformer is used for impedance matching, even it is equal to the load value, that is loudspeaker impedance value. Fine. Next, what is PD max? PD max can be obtained by making PAC is equal to 0. Yes, PAC is equal to 0. To make PAC is equal to 0, what do you have to do? What is PAC? Vm Im by 2. It implies Vm is equal to 0 or Im is equal to 0. So if you substitute Vm is equal to 0 in this, in PD, totally your PD becomes 0. So you can't find PD max when PAC is equal to 0. So for that you have to go for some alternative. That alternative is PD max can be obtained by going for dPD by dVm is equal to 0. Okay, simply take this PD and differentiate it with respect to Vm. So what you're going to get is you're going to get 2 VCC into pi RL minus 2 Vm by 2 RL is equal to 0. It implies you're going to get Vm is equal to 2 VCC by pi. Now substitute this Vm in this. You're going to get, if you substitute, that becomes your PD max. So what is PD max now? 2 VCC by pi RL. In the place of Vm, you substitute 2 VCC by pi minus Vm square is 4 VCC square by pi square into 1 by 2 RL. Okay, so if you solve it, you're going to get PD max as 2 VCC square by pi square RL. Okay, so this is the PD max. Now we'll do some calculations. What is PAC? PAC is Vm square to RL, Vm square by 2 RL. So you can now write PAC max as, yes, PAC max is Vc square by 2 RL. You'll get this VCC square by 2 RL by assuming maximum swing for Vm. Okay, you verify the last video, the maximum swing value for Vm is VCC. So you'll get this PAC max by assuming maximum swings for Vm. So it is VCC square by 2 RL. Now what is PD max? This is PD max and this is PAC max. If you observe the two, you can express your PD max as 4 by pi square PAC max. In the place of VCC square by RL, you substitute 2 PAC max. So you'll get 4 by pi square PAC max. Okay, so what is this PD max? This is the maximum power dissipated by both the transistors. For single transistor, yes, that is PD max per transistor is equal to, yes, this half of 4 by pi square PAC max. So that is 2 by pi square PAC max. So what is the conclusion? Conclusion is, what is the value of 2 by pi square? 2 by pi square is approximately equal to 1 by 5. Means maximum power dissipated per transistor is approximately 1/5 of maximum AC output power. Okay, I'll repeat. Maximum power dissipated per transistor is approximately equal to 1/5 of maximum AC output power. Okay, so this is the concept of power dissipation in the case of class D push pull. Okay, now we'll move to the harmonic distortion concept in class B push pull. Coming to the harmonic distortion in class B power amplifier. Yes, we know there are two currents as there are two transistors. One is IB1, that is, assume it as IBM cos omega t. And IB2 is in 180 degrees phase with respect to IB1. So you can call it as minus IBM cos omega t. So you can write it as IBM cos omega t plus pi. Okay, now what about the output currents? These are all, these two are input currents. Then the output currents are, first I'll write IC1. In the concept of harmonic distortion, you can assume IC1 as G1 IB1 plus G2 IB1 square because of the nonlinearity of the transistor. So if you substitute, I'll get the form B0 plus B1 cos omega t plus B2 cos 2 omega t. If you add another term G3 IB1 cube, you are going to get some B3 cos 3 omega t plus etc. Same way, if you write IC2, assume it as G1 IB2 plus G2 IB2 square plus G3 IB2 cube. Yes, substitute this IBM cos omega t plus pi in this. You're going to get B0 minus B1 cos omega t plus B2 cos 2 omega t minus B3 cos 3 omega t because it is having some plus pi phase shift. Okay, this is actually the AC currents IC1 and IC2. These two are due to the input AC currents. In addition with that, we have another DC current ICQ. Actually, you have to add that ICQ to this IC1 and also to this IC2. Okay, even if you add that, so before this, you add this ICQ for both. Because I told you many times, yes, the currents varies in the form of given input signal, means in the form of sinusoidal, but with an average value. Base currents varies with an average value of IBQ. Collector currents varies with an average value of ICQ. And the output voltage VCE varies with an average value of VCEQ. Okay. Yes, that is the reason I added this ICQ. Now, in the class B push pull, what is IL? IC1 minus IC2. If you subtract IC2 from IC1, then ICQ minus ICQ cancel, B0 minus B0 cancel, B1 cos omega t plus B1 cos omega t. So it is 2B1 cos omega t, and B2 cos 2 omega t minus B2 cos 2 omega t cancel, B3 cos 3 omega t plus minus of minus B3 cos 3 omega t becomes 2B3 cos 3 omega t. Okay. Suppose if you go for other next terms, then you're going to get all the odd harmonics along with the fundamental. What is this? This is the fundamental. And this is odd harmonic. It goes on, you're going to get odd harmonics. Means, what does it mean? It means all even harmonic components gets eliminated. We have only odd harmonics in the output of class B push-pull amplifier. Okay. Another important point is second harmonic is also an even harmonic component. As all the even harmonic components gets eliminated, yes, you can say the second harmonic component is eliminated. Fine. You know, among all harmonics, second harmonic is having highest amplitude. With the class B push-pull arrangement, we are able to eliminate the second harmonic, means we are going to eliminate much of harmonic distortion. All the remaining odd harmonic components are having very less amplitude, so we can say the harmonic distortion is eliminated a lot by this push-pull arrangement. What are the distortions now? The first distortion is percentage D3, that is mod B3 by mod B1 into 100. Next you are going to get the odd distortion D5, that is mod B5 by mod B1 into 100. Okay. So if you goes on, then you're going to get all the odd harmonic related distortions. So the percentage total distortion, is, yes, D3 square plus D5 square plus D7 square, etc. into 100. Okay. So that is percentage total harmonic distortion. Okay. So this is about class B push-pull harmonic distortion. Now in the next video, I'll do complementary symmetry class B power amplifier. Thank you very much.